are derived or how the equations are obtained, and what is the basically objective. All experiments are associated with some objective, so one must understand those things very clearly. And after doing the experiments, for example, you have done some experiments, you have collected data, maybe pressure drop or volumetric flow rate. So what we are going to do, that is very important, and that is very important. After that, when you are suppose going to write the report, so in this particular online laboratory, report writing is something very kind of doesn't make sense in that way that you have not done the experiment, still we have asked you to write the report. But at least you look at this thing in this sense that you have got some equations, you have got some observations and data. Now you try to see whether the those particular data are really worth or really making sense in that, whether they are verifying their equations, how much off from the original results or the equations lines. So those things you will get some idea. So that is why this session has been conducted, and we have taken some old data. One must check whether those are correct or not, and regarding the objective, whether we are able to get those kind of things. So in that way, earlier what we have done in the previous session, we have discussed the outline of those experiments, and after that Professor Manojit Chakraborty took a class on Peter tube experiments. So he had explained in detail. So after that, in the meanwhile, I have uploaded some documents, some Word documents of each of these experiments, which had some details, some experimental procedure or the apparatus used or the observation table looks like in that way. Hope you have seen that. So after this, let us go into by now you know that what you have to do in the Peter tube experiment. So similarly, let us see what we will be going to do in these two experiments: packed bed, fluidized bed, and pipeline viscometer. So let us first start with packed bed and fluidized bed experiment. So let me share with a few of the documents. I mean, I would try to explain the equations and what the objective part, and then I will show you the observation table data and how to write report and what are the things that are to be included in the report. Are you able to see this? No, no. Can you see this flow through packed bed, this page?
Yes, sir.
Okay, nice. Okay, so see, packed bed is a very versatile area and topic, and chemical engineers are very used to with this packed bed thing. It is considered it as a, you have studied in fluid mechanics that there is a empty tube or there is a uniform diameter tube, uniform cross section, so straight pipe or tube. Depending on the thickness and whatever. So basically this packed bed is nothing but characterized as, consider it as an empty tube, but afterwards you add some packing material. So this packed bed are typically found in lot of separation process, distillation column and absorption column, even in a large industrial this kind of reactions. Let's say this ethane dehydrogenations. So this C2H6 that gets converted to ethylene and hydrogen. So these are this is one example that I've given, dehydrogenation reactions. Similarly, much of this petrochemical industries reactions, let's say what is called reforming or cracking. So one very common experiment or example I can give you, that FCC, fluidized catalytic cracking. So we will explain that fluidized bed operations after this packed bed. So these two together, packed bed and fluidized bed, these operations are very common. That is the main thing in chemical engineering industry. So one must understand the hydrodynamic or fluid flow part. I mean, how the flow happens and what are the considerations that one need to make. For example, when the fluid flows in any empty tube that you have seen, you have understood the this genesis of the Hagen-Poiseuille equations, or the how to calculate the pressure drop. Now you will agree with me that pressure drop that is accounted in a empty tube or empty pipe, I mean uniform cross sections, will not be the same, or characteristically they will be very different when there are packings. So packings can be of this kind of what is called uh, this kind of circular diameter or spherical packing we often call, or sometimes they can be, so this is spherical packing. Sometimes they can be cylindrical. Sometimes there must be some irregular shaped. So there are many of the industrial used packing materials are available. Probably you have heard of the name called Raschig ring. So the characteristic of Raschig ring is that it has this diameter and length are equal. So L equal to D. So if this being the D, this is the L. So it's a cylindrical packing. So there are many of this type of packing that are used in the pack bed. Now there are reasons why packings are used. I'll just touch upon, but I'll not go into the detail. It actually increases the contact between two medium. For example, you are doing separations and you are using gas and liquids. So gas liquid contact must be increased. So packings are used. Now when you have packing inside this, let's say some irregular shape packing, now you will agree with me that, or rather you can think of that a flow through this packing, let's say it is going, gas is flowing through this and liquid is coming from top. Now this flow through this packed bed will not be the same as flow through empty tube or empty pipe. Let's say vis-a-vis we do keep a empty tube. So it is very much uniform and you know how to calculate the pressure drop. But when there is a packing, the things become very different. First noticeable difference that comes into our picture is that flow path. Flow path is no longer remains this kind of uniform or straight. It becomes very much tortuous. There is something called tortuous. I think you are just check the spelling. I may be making mistake. So it is basically path is not straight. It is some kind of crooked or a different shape. So it has to travel a longer distance. Fluid has to travel a longer distance. So accordingly, the delta P will be a function of these factors. Moreover, this packing materials, when they are inserted into this, these are all solid packing material, right? So when they are inserted into this box or into this diameter of this, I mean pipe, empty pipe, so then what happens? That earlier all the thing was void. I mean void fractions are basically the porosity you can consider in an empty tube is 1. But in case of packing, when it is inside the packed bed, the epsilon factor, that is the volume of void by volume of solids plus volume of void, that means total volume of the tower, that becomes very different. I mean, so depending on the packing type or packing material, epsilon, that factor can vary from 0.4 to 0.6. So that is another important consideration that you have to make. Third is that what is called what is called this A, that is the AV, sometimes we call AV, that is the interfacial area. So the unit is very interesting. It is meter square per meter cube of the bed volume. Sometimes you will find that feet square. So that means what? That this packing material, they are associated with some surface or outside area. So some interfacial area. So why interfacial area? Because this is coming in contact with the liquid as well as gas. So this interfacial area plays a big role in what is called calculation of pressure drop. So when I will explain, or when I will show you the equations, you will find lot of terms, lot of parameters. So that's why I have started with this, introducing you with this different kind of parameters. So this is very important, AV. So interfacial area of the packing material. So it is expressed as meter square of the surface area by meter cube. Now, gradually, I mean, we will see that other parameters are also there. One of the another important parameter is the dP. So that is the fourth consideration, that noticeable difference compared to empty tube. Now, in empty tube, we all know that the Reynolds number is a pipe Reynolds number or tube Reynolds number that is expressed as rho V D by mu, or sometimes called rho into V, that is often we write as G, or mass gas mass velocity or liquid mass velocity. So G into D by mu. Now what is this D? D is basically the diameter of the tube. Now when in the packed bed operations, this D is characteristically very different. Now this D is no longer remain a diameter of the tube. It is basically diameter of the particle. So that is of which particle? It is basically the packing material. Now, depending on the shape of the packing material, whether they are spherical or cylindrical or any arbitrary shape, so then dP becomes different. So, and accordingly, we define particle Reynolds number, that is REP. And this, whether they are in flow is in laminar zone or turbulent zone, it all depends on this REP. And since you will understand, or you see that it is no longer the pipe diameter, so that range, that 2300 or more than or less than, considering turbulent or laminar, no longer remains valid for particle Reynolds number. So these are the noticeable differences we often see in packed bed operations. Now, we before coming to this kind of big expressions, which we often see, this kind of expression we see, we call it as Argon equations. There are many terms. I will tell you which term means what. But before that, let us try to understand how this equation is coming, at least through some general idea. Let us try to make. Okay. Now you will agree that when flow is encountering a solid object, or flow past what is called object, flow past a solid object which is immersed in that phase, is basically what we call, we see in some kind of drag. So drag force. So this we would start with this drag force per unit area of the surface, that and from there we will go to the pressure drop expressions. So first consideration that we make is that these two, basically it is flow path is basically a tortuous, and actual beds are basically not only this regular shaped particle, but they are very much irregular sized particles. Second, other two consideration is that how do we derive this, or what is the starting point? Now we all know that this Hagen-Poiseuille equations, or in a pipe flow which is of uniform cross sections. So there what we do, we have derived the expressions from starting from Navier-Stokes equations, or you can consider the momentum balance of over a small volume element, and balance the and start and derive the equations with the expression of this pressure drop equals to the pipe diameter as a function of pipe diameter. And noticeably that you will agree that in laminar zone it is proportional to V, and turbulent zone it is proportional to V square, the pressure drop. So that consideration had had the thing in with us is that the cross sectional area of the flow is uniform, or there is no such hindrance or blockage by the particle. Here we would assume that the actual flow channel in this kind of packed bed, it is basically we make an assumption that this actual flow is replaced by the parallel cylindrical conduits of constant cross sections. Now, you would probably not agree with the fact that we have told that there is some void fractions and porosity. So these factors we will take into account. But for the for writing this drag force expressions or this kind of similar to that Hagen-Pauli starting equations, or in order to draw a resemblance of this packed bed and empty tube consideration, we consider that flow path is replaced by parallel cylindrical conduits. So actual flow path is no longer remain the straight, but we consider it as to be the straight, and then we take into account the other factors, that is epsilon, tortuosity, etc., etc. And as this pressure drop, they consist of two different terms, which is depending on the which one dominates, inertial and viscous, I mean as a function of Reynolds number. So these two are important, and we propose an expressions that it is proportional to v and v square for laminar and turbulent. So through that we proceed and we start to calculate this k1 and k2. Now this K1 and K2, these are basically parameters or some kind of constant that comes after we fit these expressions through some experimental data. So K1 and K2 has been tested and validated over packed bed operations, taking into many different kind of packing material and different flow operations, and they have been fitted and we have got this kind of constant number, that is 150 and 1.75. So I'll just tell you how this equation has been obtained one by one. So typically we do not start with a pipe diameter. Rather, we are interested because there are some packing materials are available, and we start with the hydraulic radius, that is RH. So in the case of hydraulic radius, we write this expression as cross section of the conduits by weighted perimeter, and then we just multiply both by length of the bed. So suppose this is the length of the bed, which is L, and then this goes to this kind of expressions. So you would just follow this, and you will find that we introduce somewhere as the surface area of one particle. Now this expression is very important. I think there is a wrong in this expression. It would be SP by VP. So this will go up. So this is actually required for your DP calculations, diameter of particle. Now phi p is basically the shape factor, or oftentimes we write it as phi s. So it is basically sphericity or shape factor. So this dp calculations comes from here, and epsilon is basically the porosity or the void fractions. So this you just go through these expressions. It is not also possible for explaining all the things in this particular short time, but it starts with this, as I said, it starts with these two assumptions, and total pressure drop we equate to viscous and inertial, and then in the final expressions we see that this is a one part corresponds to laminar zone and other part corresponds to turbulent zone. In the final expression, you see that there are different terms, which epsilon is basically the bed porosity or void fractions, dp is the particle diameter, phi s is the sphericity. So if it is a spherical particle, then it is 1. If other shaped or cylindrical, then they are less than 1, and there are basically charts available depending on the packing type and their corresponding phi s. So through these expressions, you would basically validate the experimental data, whether you are getting delta p by L as so basically delta p by L delta p rather you are measuring from experiments in packed bed expressions, and also you have the data available with you. For example, rho, epsilon, dp, phi s, all are available, and you just so one is the experimental delta p and one is the delta p obtained from theory. One is experimental delta p and one is theoretical delta p. So you just try to see a match, whether you are getting a good match between them, you can also draw a plot and see how the, like a parity plot, how they are different or how close they are. So over a range of Reynolds number, or let's say velocity across the bed, you can plot the delta P. So delta P of this, what is called pressure drop across the bed, as a function of Reynolds number. And one may extend this idea to also calculate the friction factor across the bed. So these two are essentially it is required in case of packed bed expressions. And I will just show you the observation table. How does it look like? So that would give you an idea that in case of report making, how to go about that. Okay, let me. Okay, this is. Okay, so fluidized bed will just come after some time. So this data were collected. Now, interestingly, I would say that last year I had done some video of this packed bed experiment. So that I will upload in the file section. So you please go through them so that you can get an idea that how the data were collected, and some description of the equipment was shown. Probably you have seen in one image of the packed bed was shown during the first class, but seeing the video would give you an overall better idea. So I will upload that. It's a big file size, so it will take time to upload. So after the class I will upload and you go through the video. So the experimental details and experiments were carried out. So that is. Now this one thing you agree that there is a flow rate of that is associated with this experiment. So you have to change the different you have to collect the flow rate, or you have to calculate the flow rates. So you can basically take different fluid mass that is collected at particular time interval, and you vary basically the flow rate. So we are not using any kind of rotameter or any experiment through device through which we are varying this, but we have a basically valve operations. So through which we turn the valve to a certain point or certain turn, and then we allow the flow to happen, and then we measure the flow rate. Then we again change the valve to a different turn and increase it. Like that, we basically collect a different flow rate. And according to and at that particular point, we also allow for some time to flow go attain a steady state, so that we can measure the pressure drop in the manometer. So that through that we actually take the delta P and the flow rate. So if you know the packed bed area or the cross section, then you can also calculate the velocity. So through that we and that velocity is what? That velocity is empty tower velocity. So we have to convert that velocity into what is called packed bed velocity. So we often call the empty tower velocity, which is denoted as V naught, as superficial velocity. So you have to convert that into empty packed bed velocity by taking into account the epsilon factor. So those things are there. You have to consider them in the equations, and you have to use that, so that ultimately you get a packed bed delta P experimentally and theoretically. And then you try to see whether you get a good match or not. And also you can extend the idea that you can also calculate the friction factor, as I have showed in the expression last slide or last PDF, that friction factor versus Reynolds number. And typically what is the plot of friction factor versus Reynolds number? You have all seen the Moody's chart or Moody's expressions. So that let me just draw qualitatively. Maybe I change the slide once more. So suppose you uh, are doing a so that is one plot, delta p versus Reynolds number, or parity plot, basically delta p experimental, delta p theoretical. So that's that two thing you can do. So delta p theoretical and delta p experimental. Another plot you can make, which is friction factor versus Reynolds number. So you can see that whether you're getting this kind of, so one is the laminar zone and another is the turbulent zone. So this kind of expression you just try to validate, you just try to see whether the data are giving this kind of expression or not, and how much off it is from the theoretical one. So you can draw some inference that what could be the reasons, or though you haven't performed the experiment, but from the common sense or some idea about the manometer reading corrections or manual error or some human error. So this thing you can write down. So these plots are essential, so they must be there in your report, and since it is coming from the data available, so you must make a note of it. You must do these exercises, so it will give you a fair enough idea about what is the equations plot or equations data, and basically the actual data. That is the packed bed thing I would explain. And then at the same point, we have also this fluidized bed operations. Now fluidized bed operations is nothing but it is an extension of packed bed operations. So suppose you have the same fluidized bed yeah, packed bed thing. You have this packing, different packing materials are there, and you are operating it under fluidized condition. Now one would imagine that in the packed bed, when there is a liquid flow and there is upward or gas flow, the packing remain constant. I mean, packing materials do not change their positions, they are fixed at a particular place. So that's something we often see, that fixed bed. That term we have heard, that fixed bed operations or fixed bed reactor operations. So when the packing material, we just allow them to be remain fixed, to remain not unchanged, or to remain static, then it is a packed bed operations, and we have a standard delta P. Now when we have packing no longer remains static at their place, they are basically going up and down, they are changing their positions, they are basically moved from their place. So how do we move them? How do we, and rather, first of all, why do we need them to move from their place, and how do we do that? So fluidized bed operations are very common in also industry, as I said, considering many separations or adsorption or basically catalytic cracking, fluidized bed catalytic cracking, that is FCCU, naphtha cracking. If you go to or if, you will see that in refinery, naphtha cracking is a very big unit, petroleum refinery. So naphtha cracking, this fluidized bed operations are used. Now there are many advantages of fluidized bed operations. One advantage being the using of packing material, but when the packing materials, or in case of fluidized bed catalytic cracking, when it is FCCU, fluidized catalytic cracking unit, the packing material are basically the catalyst, or catalyst are basically are the packings. So those are basically moved, they are rotated, they are circulated, they are no longer kept static. So what advantage do we get? We get in typically fluidized bed operations a high rate of transfer, mass transfer or heat transfer. So that are actually very essential in heterogeneous kind of reactions. So good heat control. I mean, in packed bed operations or fixed bed operation, we often encounter hotspot. That is not desirable in operations. So in order to overcome them, the bed are treated as fluidized. So let us try to understand what is fluidized, or what is the term meaning called fluidized. We just have a medium to cause or to move them, for example either gas or liquid. So we take that to move the particle from their static conditions, and we treat the whole bed, or we encounter a situation when it looks like that the packing materials or the solid particles, they are moving, they are vibrating, they are kind of like dancing on the at their positions. So a common examples, I mean, just to visualize this, if you have taken a boiling water, or let's say you have taken water and you have just added rice on it. So after some time you will see that water boils and some of the rice are coming at the top, and they are going up and down, they are vibrating at their positions. So that means that what, there is a solid that is basically treating as, or behaving as fluid or fluidized. So the whole bed is going as a fluidized. So in a layer of packing, only when the flow is going from the low to bottom, low to top, I mean bottom to top, the first few layers will move. They will be moved from their positions. As you go on, increase the flow rate of that medium, maybe gas or liquid, from the below, gradually the second layer also starts moving. In this way, all the packing material, they will move, and it is like a whole bubbling operations, or when the water boils, you have seen that bubbles form and they coagulate and form big bubbles. So here also the the solid materials will start moving from their positions, and in the whole operations they will behave like moving from their positions, and that allows a very faster heat control. That means if the reactions is very much exothermic, or if heat distribution remains to be achieved, then this kind of operations are called for. These times of kind of operations are required. So that fluidization's conditions one needs to ensure. So that's why we are interested to understand what is, or we are interested to see from the experiment, that what is minimum fluidization velocity. So that is called VMF or UMF in the expressions you will find out. Now, what is the basis of that obtaining that equations or expressions? Now, as I said, that it is an extension of packed bed operations. That means before fluidization happened, or let's say the flow rate of the, or mass velocity of the gas or the liquid is not sufficient. So then what is happening? It is still at the static conditions. The bed is static. There is a continuous, I mean, there is a constant delta P, or there is a delta P at that particular flow rate, right? So as the flow rate becomes more, or it crosses some threshold, or it crosses some limit, so that limit we are calling as this limit. So once it crosses that limit, the bed tries to move, or rather the particles tries to move from their positions. So then the delta P, then also there will be a delta P, but uh, what causes them to move? That means when the bed was static, there was a weight of the solid particles, and there was a buoyancy force. So if you make a balance of that, just when the onset of fluidization, that we call the onset of fluidizations, that then what happens? Just it almost that the incoming, the pressure drop that is there in these directions, and the weight of the bed is also in these directions, and also you have the buoyancy force. So this all together, you will see that they just kind of make a balance to almost at this point. So just before the fluidization, we equate them. To know that what will be the VMF. Now you will agree that the delta P is a function of VMF, or rather V, of flow rate. So, or the velocity, minimum fluidization velocity. So it's a function of velocity of the gas or the liquid. So at that balance condition, when the bed is almost about to start its movement, or when the packing materials are about to start their movement, so that velocity we need to achieve. So that is called VMF. So the very same expressions will be used for delta P, and since we are measuring delta P in fluidization operation also, so we don't need to, rather we will take that and use in the expression of the delta P. So that way we go for VMF calculations, and here you will see that we have equated this solid particles and buoyancy force to the pressure drop expressions, and ultimately we will find that what is called yeah, at minimum fluidization conditions, so this equation happens. So you will agree that there is the bed porosity that was also constant before the fluidization happened. At the onset of fluidization, there is a minimum bed porosity. So there is a minimum fluidization velocity. So that thing we are going to calculate from this experiment, or that thing we are going to measure from this experiment. Now, this in our laboratory here, we use the sand materials. So sand is also used in some applications, but this packing materials that I have said that they could be pearl saddle or ball saddles. I mean, the small packing materials are also used. Different kind of packing materials are used and tested for minimum fluidization velocity. So you basically take the same expressions and all the V are replaced as VMF, and then you just equate to the weight and buoyancy force, and ultimately you get the epsilon MF or VMF. Okay, so that expression or that equation is this equation is required for calculation of epsilon VMF and epsilon MF. So qualitatively, what we understand that when we have a let's say this is the velocity and this is the delta P. Now, as long as the fluidization didn't happen, there is a continuous rise in delta P with the velocity. The moment there is a fluidization achieved, there is a equate them with the balanced conditions, and after that there is, you will see that there is some drop, and then it remains constant. See, these operations are carried out in a bed, so particles are not allowed to leave, right? They could be entrained, or they so let's say up to this height, the packing materials are there. So they could be entrained, like when the force is rather when the velocity or the volumetric flow rates of the gas or liquid is high enough that it takes away the particle from its positions and go to its top, and then it again falls back. So that is the extreme condition, extreme fluidizations. So that entrainment part we are not taking into account. We are just considering that when the bed was just at these positions, when the particles were not moving, that means the static part, when delta P versus Reynolds number or velocity. Just after the fluidization or at the onset of fluidization, let's say this point is achieved, and then you will see some drop. This is a very interesting observation. Why I am saying, because the data that has been provided, when you will plot or when you will go for, you will see this kind of behavior. Now this kind of behavior is very important to understand. Why it is happening? See, at the point of fluidizations, they are just about to move, they are just about to vibrate on their positions. So what happens? Earlier the bed was static, there was a constant epsilon, and they particles were almost attached to each other, or they were just behaving as intact, no movement. But at the point of fluidization, when it happened, some expansion of the bed happens. We call the expansion of bed. Now what do we mean by that? That means these particles were no longer remaining at their position, so they move. Now during that movement, there is some expansion. That means there is more of the void fractions. Now epsilon is more. So the movement of that allows temporarily the void part or the void volume to be more. Now if you have more of the epsilon at a particular instant, then delta P is little bit changes, delta P little bit drops, because if you have a very large voids, then you don't have a much pressure drop, right? So that part is basically this part, when the bed is going to adjust themselves. That means when the first few of the layers of the packing materials are about to movement, and others have not yet moved. others are remaining almost static. Now this will happen in a very small range of V, that is not very high range, right? So over a small range of V, when the bed is going to be adjusted, that means at the first instant some layer or the first layer of the particle will move, others will remain static. At the very next moment, the second layer, third layer, and in this way all the layer of the particle will move. So when all the layers have started to move, then there is no more uh, after that there is no more change. That means we call the fluidization has totally been achieved. Fluidization is, the bed is behaving as under fluidized conditions, and then delta P is no longer changing. So that part is very important to understand, that initially bed pressure drop was there. As the velocity increases, bed was static or fixed. During fluidizations, first layer of the particles behaving to move. After few layers, after certain little bit increase in V, the others are also started to move. So during that time, what is happening? More of the voids are coming at an instant. More of the void volumes are exposed. So that causes a little bit dent in the delta P. And after that, once all the beds are fluidized, then it is more or less uniform. Then it means that bed is now conditioned. Bed is now almost like all the particles are moving in the same manner, so it is under fluidized conditions and no more change in the delta P. It is so what will then happen then at that point also epsilon will not change. Here also epsilon was not changing. Now during this instant epsilon will little bit increase, right? So that increase in epsilon is equated as these expressions. So that happens when delta P is no longer changing. Delta P is almost same. So L so expansion of bed is associated with increase in what is called epsilon. So bed height little bit expands. So as I said, so this height little bit expands along with the expansion of epsilon, and then almost like when all the beds are fluidized, then there is no more change. So that is this line. Or but in experimental observations, it is very hard to get this kind of constant. You will see some little bit up and down in delta P. So always one needs to be very careful about measuring delta P experimentally. So this experiment also, let me show you the what is called observation plot. Mm. So you also see that this flow rate and bed height are given, and also the pressure drop is also given. So bed height means the L, that L part is given to you. So from the flow rate you have to calculate the velocity, and you have to mark or identify experimentally from graphically that what is that point of fluidizations. You may not to be required to use the expressions to calculate VMF, but given the data, you will be identifying from the experimental qualitative plot, as I just explained, that what is that point, what is that particular flow rate or velocity at when the bed is fluidized or just about to fluidized, so minimum fluidization conditions. So that part you try to see whether you can do that or not. And qualitatively, when you plot it with respect to velocity, the height and pressure drop, then you will understand the operations, that static part and the fluidized part. Just I explained from the plot. So this is the fluidization in table, observation table. Okay, so I'll just take a little break in now and see some clarifications, or if you have, I will upload this experimental table, observation table, or at the same time the video that I had over backbed. And interestingly, I would also share for your own benefit, own understanding. I had some backbed and fluidized bed operations which I had done in my time, or rather that there is a report on full-fledged this backbed fluidized bed operations. So the reason I am sharing with that you can also see that they are of course a different data set. There is no match of that. But having that with you will help you to understand how this has been done. It is almost like an example problem is given and then you are asked to do some exercise problem. So this plot I have, this report I have thought to share with you, but I don't have the other kind of reports for, you know, Pitot tube or Bernoulli. But this packed bed fluidized bed, I consider that we are compared to other experiments, it's little bit more exhaustive and difficult, or compared to it is more elaborate and large. So I thought that I would also share that with you. Okay. So couple of things I will share after the class. So don't worry about that. Now, if you have some quick questions, then I can address. Okay, no more question. Okay, so let us touch upon the other experiment, which is pipeline viscometer. Let me also tell the objective part, what we have to do in pipeline viscometer, and then basically you will see the observation table and you try to calculate from the observation table about the parameter or the constant that you have to calculate. Now, see, in real experiment or in real situations, we take into account a kind of what is called viscometer. So there are different type of viscometer. One common use is that Asphalt type viscometer. So initially in our there is frankly tell you that in this experiment the name is also given pipeline viscometer. Okay, but this pipeline viscometer we are not particularly using any viscometer. Okay, in the picture or in the image that is shared in the folder in the file section, you will see that there are continuous different type of pipe. I mean different length, different diameter, and on one side you have the control valve to operate the flow to calculate the volumetric flow rate, and you have also manometer attached to that particular cross section. So let me just open the image, so it would be better, I think. Maybe we have to at some point of time change the name of the thing, because in really we are not using any viscometer, but over just a straight pipe and trying to validate the Newton's law of viscosity, or the fully developed flow, what is the pressure drop and shear stress, wall shear stress. So just quickly I will share the image just to bring you highlight. Just to highlight this. Okay, you just see that we don't see any Asphalt viscometer. So typically viscometer looks very different. I mean, on one hand you have a straight portion, other hand you have some uh, uh, increased diameter, some kind of cylindrical section where you consider the time it takes to rise that particular portion and to calculate the viscosity. So Asphalt viscometer is altogether a different operations. So viscometer principle, working principle, we are not considering at all. So please be remembered that this experiment is not about how a viscometer operates. Rather, this experiment was made in a simple manner just to ensure that there are different type of diameter of pipe. So one is a very large diameter compared to that less, and even less, and further less. So this 4 different diameter of the pipe was taken, and you have the manometer attached to a particular section or particular portion of the pipe, where you are basically calculating the pressure drop and what is called flow. So the length of the pipe is high or very large in order to ensure that we remain at the fully developed flow conditions. So you all know that what is fully developed flow, that where pressure across the flow path is no longer a function of y, or rather it is fully a function of x. It is fully a function of x, no longer function of y, and velocity is no longer function of x, but it is a function of y. So what we are essentially doing, we are essentially doing the wall shear stress, delta P, and viscosity. That means we are trying to measure the viscosity of water. That is the objective. How we are doing? We are trying to validate by constructing an experimental way, so that this what is called a laminar flow or fully developed steady flow over a cylindrical pipe, that the expression gets validated. So let me just remind you, or with that expression, that would be easy to understand at this moment. So I had that also. What is called okay, I think you can see this. So all in all, we are trying to do the Newtonian fluid experiment, or taking a Newtonian fluid. So we have just taken water, and we are trying to use this or rather validate this uh, expressions and calculating the mu. That's all in all we are doing. So apparently it looks like that it's easy. I mean, we are not measuring the du dy, but we are measuring some other quantities through which we can calculate du dy and the tau w, wall shear stress. Now these expressions, which is basically the what is called laminar flow, sorry, earlier not this one but this one, laminar flow in circular pipe. So these expressions you are familiar with. You are familiar with these expressions, where you get a velocity profile of this kind, and you know what is called wall shear stress, tau w. So this tau w expression is related to what is called delta p by l, delta p by l. So that part is you have understood in your fluid mechanics course, that I will not discuss here. So essentially tau w and delta p are equated, and through delta p, since we are measuring through manometer, so getting the record, so tau w is essentially calculated. Similarly, the du dr, that expression is also calculated with other observables or other parameters, for example this q or r or something. So all in all, we are, instead of measuring directly the shear stress and rate of shear, we are calculating it through the other measurable quantity and actually finding out the constant, that is mu. And that for that we have taken a different diameter of tube. That means one is more larger, then other is smaller. So 4 different diameters, just to make sure that they get validated, and more number of sample size or kind of operations would give you a better enough control or idea that mu of water, how does it do. So typically mu of water is 1 centipoise. So from that data, we try to come to that particular point, that whether mu is how much is the mu of water. So of course the experimental results are associated with some kind of error. So how much off from the original or the actual one. So if you take Asphalt Viscometer, you will more or less get 1 cp. But here in this experiment, though it says pipeline viscometer, but it's actually not a viscometer. It is basically a just taken a straight portion of the pipe or tube and varied. We have varied the diameter, varied the length, and just taking that particular thing to calculate delta p and other measurables like q. So through that and we know that L, rho, these things we know. So through some quantity measured, we are just calculating tau W and what is called DUTR. So after that, we are just equating them, or rather plotting them, and then calculating the slope of the curve to get the mu. So it is basically validating this laminar flow in circular pipe. Please be remember that it is validating that, and ultimately we are calculating mu, so which is basically constant because it's a Newtonian fluid. So this is that experiments, and not much to say about this experiment, is just to see what you have to done, what you have to do, and just I will show you the observation table, and then things will be over. So observation table of what is called pipeline. No? Okay, so this part. Okay, so you see that again, so this mass collected and time, it is basically a flow rate. We are all in all doing the flow rate. We are just taking empty bucket and then operating the valve to increase the flow, decrease the flow, and accordingly we are just taking a series of runs, 4 or 5 different data. So this it's very crude way of calculating. I mean, a lot of error remain get basically associated with this, but that's how, I mean, we do in typically, less expensive manner, or just to understand that how the things go. But gradually you can go for sophistications. You can add a rotameter, you can add a flow measuring device to go for betterment. So this flow rate you basically calculate. Also you know the pressure drop, and then from that you basically calculate the delta P. So this sometimes you will find that there are some mistakes in the manuals. I mean, it is, let us admit the fact that it was made long time back. I mean, we have to, frankly speaking, make it correct. But that's why I'm saying here that, for example, it is not P, it will be delta P. So delta P is what? Delta rho delta H into G. But again, it is some kind of 100 kg force per meter square. So don't be confused with this thing. I only want to say that all in all, you know how to calculate delta P, and it is basically the difference in height into difference in manometric fluid density into G. So remain associated with the SI unit. Don't go for kg force per centimeter square and like this. It will make you more confused. So calculate delta P. Expression used for tau W and DUDR are known to you. Also, you check the expressions from standard book, fluid mechanics book, because this laminar flow in straight pipe is very common. You will find the wall shear stress, you will find the average rate of shear, DUDR. So basically, once you know the U expression of U, you can calculate DUDR average, and tau W is also equated to delta P, wall shear stress, because that the formalism of that expressions, or tau at different points. So through that you can come up with this viscosity measurement and Newton's law of viscosity validations. So we are all doing the measuring the viscosity of water. The fluid that is flowing through the pipe is water. So sometimes we can change the fluid. We may measure the oil viscosity or something. So we can see some different noticeable difference will come in terms of delta P and what is called flow rate or something. So viscosity of water are not the same as the viscosity of oil. So viscosity of oil can also be measured. So those variations can always be done. And this is what you have to do, different table. Okay, let me show you the not this observation table. Okay. Let me this one where actually the data are there. I was confused with this. Pipeline Viscometer. Okay. Okay, so this was basically you have seen in the image I had shown that there were 4 different pipes. So pipe 1, for that particular pipe we had taken 5 different readings. That means 5 different volumetric flow rate and 5 delta P. So from here you will get a mu. Similarly, for pipe 2 also you will get. Pipe 3 also you will get pipe 4. Now mu of course doesn't depend on the pipe, doesn't depend on the pipe length or something. So you will see that they are almost close, or they are just see from the calculation of the data how the mu is coming, and then you kind of do an averaging of that and report that particular thing. So even one pipe is also fine, but we have just taken to change the diameter and length, not the length change, the diameter, but to see the variations, or if mu are really varying or not. I mean, it should not vary if you perform the experiment in that way. But of course, the mass collected and time, these are very much prone to erroneous results or erroneous data. So this part is clear. So this pipeline viscometer is basically measuring you or giving you the viscosity. In really, we are not using any Asphalt viscometer or kind of thing. Okay, so this was the thing that I wanted to discuss with you. I understand it has gone very much exhaustive, but the reason I did it is because so that you do not you do not go making for the report very mechanically. I wanted you to understand the equation. I wanted you to see how the things from where you need to write or from where you need to look. So just taking the observation table data and making a report will not give much satisfaction at this moment. At least if you understand the theory and if you know a little bit more of surrounding things, then you will be a little bit more, you will also be more involved in the process. So that's all. I hope you have all the standard books of fluid mechanics or other, so you can do more study on those packed bed, fluidized bed operations. And pipeline viscometer part is standard, this fluid mechanics course you have studied. So we are just measuring the viscosity of water. Okay, so in the theory, this part was about to tell you, convey you. I will upload the necessary files, observation tables, every details by today, and I will also create an assignment link. So it's basically, as I said, for the assessment purpose, you have to submit a report and you have to appear for a MCQ objective questions later, not now or maybe not before 10th, but sometime after 10th of June. So I will create a deadline of around 10th or 11th June to submit the report of this 4. Don't make very elaborate report. Don't go for it. I mean, just main basic things. For example, the objective, the schematic, the calculations, and the plot. This much will be enough. No need to write the theory part. We are not going to read the theory. It is already there in the book, and you also know. So don't spend much time, or rather don't spend time on writing the theory. Just mention the main things. That is the objective, name of the experiments, schematic, and the observation table that I will provide you, basically the calculations. So one sample calculations must be there. Wherever you do some observation tables, and based on that you calculate what is called mu, or you calculate what is called minimum fluidization velocity or delta P theoretical, whatever you do, show one sample calculations in each report individually. So that is very important. Individually report making, and one sample calculation will be enough, and then after that plot. And finally you summarize that, or you conclude in 1 or 2 sentences your interpretations of results, like that. Since you have not done experiment physically, so very not making much sense about writing the comments in the error part, or where it was not operating successfully or something. So don't go in that way, but at least you interpret the results, so that will be fine enough with the reports. I will give you one more guideline about maybe I will upload one thing, one page Word doc with the key points that you have to make in the report. Okay, so I think that's all for the discussion. If you have any queries, you can ask, or you can post in the Microsoft Teams this channel class that is created. So you can post your queries there. By tonight, I will upload all the necessary files along with the backbed video that I had done earlier, and one report, full-fledged report of packed bed fluidized bed. So that will give you an idea. Okay, is there any questions? Okay, if no more questions, then we conclude the day. We conclude our class, and we wait for your reports to collect, and further announcements will be made regarding the MCQ test that will be based on these 4 experiments.
Thank you, sir.
Okay,
Thank you,
thank you.
sir.
Thank you, sir.